Now let's see why transformers replaced every other AI model. Okay, I think earlier on in this playlist, when I started this playlist, right, I referred to a particular paper by Vashwani et al. That totally revolutionized the whole AI idea, talking about the idea of transformers. Let me see if I can quickly get that still. The paper was never published, it was just only on archive, and it has well over 200,000 citations. Vashwani, is it Vashwani or Vashwami? Let me see. My first instinct is Vashwani et al. I think it talks about attention is all you need. Attention is all you need. So it brought up the idea of transformers. So the landmark machine learning paper, Attention is All You Need, was written by Ashish Vaswani. Oh, it's Vaswani. It's all in 2017. It introduced the transformer architecture, which relies only solely on attention mechanisms instead of traditional recurrence or convolution. So you can find the paper on archive here. So in fact, the PDF is there freely. Uh, I don't think it was peer reviewed even. It was just put on archive, and seriously, the paper made a whole brought a whole revolution to artificial intelligence like that. So brought up the idea of attentions, transformers, and this one formula that changed the whole game. I think we've talked about this a couple of times and we'll still talk about it. Now, let's go ahead. So why transformer replaced every other AI model? So that paper led to it, right? So artificial intelligence has gone through several generations of neural network architectures. Early neural networks solve could solve only simple pattern recognition tasks. So later, convolutional neural networks (CNNs) revolutionized computer vision, which we've been seeing in the few videos we considered not quite long. So what recurrent neural networks and long short-term memory networks became the dominant models for language processing. However, these earlier architectures had significant limitations. They struggled to understand very long sequences, very difficult to parallelize, and became increasingly inefficient as data sets grew larger. So in 2017, researchers at Google introduced the transformer architecture in the landmark paper, Attention is All You Need. Rather than processing words one at a time, transformers introduced the concept of self-attention. So allowing every word in a sentence to directly interact with every other word. This innovation transformed artificial intelligence. Today, nearly every state-of-the-art language model, including ChatGPT, Claude, Gemini, Llama, Mistral, and DeepSeek, is based on the transformer architecture. So you see why transformer replaced every other model right there. So our learning objectives here as follows. After completing this lesson, you should be able to explain why earlier sequence models struggled, understand sequence modeling, explain self-attention mathematically, describe positional encoding, and explain why transformers scale efficiently. Then you understand why ChatGPT, Claude, and Gemini all use transformers. Now, first of all, understanding sequence data. Most real-world artificial intelligence problems involve sequences rather than isolated pieces of data. So a sequence is an ordered collection of elements where the position of each element carries meaning. So examples of sequence data include words in a sequence, characters in a paragraph, audio signals, DNA sequences, protein sequences, stock prices over time, weather observations, sensor measurements, and video frames. Unlike tabular data, sequence data possesses temporal or positional dependencies, meaning that earlier elements influence later ones. For example, consider the sentence, the boy who won the mathematics competition yesterday received a scholarship. So to correctly interpret the sentence, the model must remember that boy is the subject associated with received, even though many words lie in between. So the key was the boy and the receiving is and receive. So the goal of sequence modeling is therefore to estimate the probability of the next element given the previous element. I mean, we've seen this when we talk about how ChatGPT determines the next word and things like that. There's a whole video dedicated to that, or even a series of videos. Mathematically, then we say that probability x1, x2 up to xn is the multiplication, the product of all the probabilities of xt given x1 and earlier inputs like that, where xt denotes the token at a position t. Now we've talked about tokens already, that they can be whole words of chunks of portions of words that things are broken down into and assigned values. for easy AI processing. So P of this probability is the conditional probability of the next token. So what's the probability that given you already have a token X sub T, what's the probability of token X at this particular time, given other tokens before now? So this formulation forms the basis of language modeling used by ChatGPT, Claude, and Gemini. Example, suppose a model receives this. Artificial intelligence is, the model predicts probabilities such as transforming that 0.4 to changing 0.28, becoming 0.14, important 0.08, powerful 0.08. The word with the highest probability is selected or sampled as the next token. So in this case, now the highest probability belongs to transforming. So we can say artificial intelligence is transforming. So the prediction process repeats until the sentence is complete. And that's why you see that when you prompt an AI model, it gives you those words, the words sequentially, because it is following this whole idea of predicting the next word to use and all that. Now, another question, why recurrent neural networks were invented in the first place, right? The traditional neural networks assume that every input is independent, that is, they have no connections, which attention has shown us to be totally not true. So for language, this assumption is incorrect because previous words influence future words. So recurrent neural networks, RNNs, were introduced to solve this problem. So instead of processing every word independently, an RNN maintains a hidden state that stores information from previous time steps. So the hidden state is updated recursively. So the hidden state equation is then h sub t equals f of w sub h multiplied by h sub t minus 1 plus w sub x sub t plus b, where x sub t is the current input, h sub t minus 1 is the previous hidden state, then w sub h is the current recurrent weight matrix. W sub x is the input weight matrix. B is the bias vector. And F, the function is usually the tanh or ReLU activation. So F here is an activation function. I mean, we talked about the whole idea of activation function all along. I mean, what we have inside of here is actually just a linear transformation, but we need activation function to actually make sense of it. That is what introduces ideas of non-linearity and all of that. So the prediction is then computed as y sub t equals g of w naught h of sub t, where g of the function g is typically a softmax function. So softmax basically brings up the final probability that adds that tells us the attention each word should get. So imagine we have a sentence as an example. I loved studying mathematics. Processing occurs sequentially. Input is I, which you can compute h1. Input love now. Love is h2. That's f of h1 x2. Step 3 now. Studying. You have h3. That's a function of h2 and x3, which coming on. So each hidden state depends entirely on the previous hidden state. So you see, h2 is a function of h1 and then H3 is a function of H2. So this sequential dependency later became one of the biggest limitations of RNNs. So, and then why RNNs struggled, although RNNs represented a major breakthrough, they suffered, that's recurrent neural networks. So they suffered from several practical limitations. So for instance, they had to do sequential processing. So an RNN cannot process word 10 units um, an RNN cannot process word 10 until word 1 to 9 have been processed. So that sequence is important. So this limits GPU utilization. So for a sentence with 1,100 words, so you have word 1 followed by word 2 followed by word 3, and it has to go to that all the way to word 100. So every computation must wait for the previous one. That's one problem with RNN. So sequential processing. Then we have vanishing gradients. During back propagation, gradients become repeatedly multiplied by smaller numbers. So suppose you have 0.8 raised per 100. That's a lot. Then you have 0.8, which is raised per 100 is approximately 2.104 times 10 raised per minus 10. That's pretty close to zero. So the gradient becomes almost zero. So earlier, and once gradient becomes zero, so it means learning becomes total slow, or learning actually grinds to a halt, possibly. So earlier words are then effectively forgotten. So because there's hardly any kind of learning anymore. Then you can also have exploding gradients. So conversely, repeated multiplication by values larger than one causes something like 1.2 raised per 100 to become extremely large. So making optimization unstable. So you have vanishing gradients, exploding gradients in addition to sequential processing. Then we also then have long-term memory failure. So sentence, the professor who traveled around Europe for 2 years finally returned and he published a book. To interpret he, the model must remember professor for many words earlier. So standard RNNs often failed on such long-range dependencies. So when words are far apart, it becomes a problem. So there's a long-term memory failure. So connections are hard to be made between a word and maybe a word that is like that has like 500, 10 words in between or more, or even more than that. Then we go ahead and we have the LSTM and GRU, which are partial solutions to the idea of recurrent neural networks. So to overcome the shortcomings of recurrent neural networks, researchers developed long short-term memory LSTM networks and gated recurrent units GRUs. Instead of one hidden state, LSTMs introduce a memory cell together with three gates. So you have the forget the gate, the input gate, and the output gate. So the forget gate F sub t is so it applies an activation function sigma to W sub f x sub t multiplied by x sub t plus u sub f h sub t minus 1 plus b sub f, and then you have the input gate I sub t, which is sigma of W sub I x sub t plus u sub I h sub t minus 1 plus b sub I, and then you have the candidate memory C sub t, like that, and that's tanh. So the activation here is tanh. So W sub C, X sub T, and all that. And then you have the memory update, which finally now says CT is equal to F of T, the F of T here, dot C sub T minus 1 plus I sub T from here, dot C sub T, like that. Then you have the output gate also, which is O of T equals sigma of this expression. And then the hidden state is A sub T, which is O of T convoluted with tanh C of T. So this mechanism significantly improved memory retention. However, LSTM still process sequences one step at a time. So training it remains slow, especially for billions of words. So if you have to do billions of words, you needed a lot of time. So the transformer revolution now came in 2017, I believe, with this Vaswani paper, Vaswani et al. So I think. I mean, they are so important. I think I should mention everybody on the paper very importantly. So you have Ashish Vaswani, Noam Shazar, Nikki Parmar, Jacob Uzkoret, you have Leon Jones, Aiden N. Gomez, Lucas Kaiser, and Ilya Polosukin. So they brought the whole idea of transformers that changed the world of AI permanently and made it very easy. So the transformer architecture completely changed sequence modeling. So instead of remembering information through recurrence, the transformer allows every word to directly communicate with every other word. So this mechanism is called self-attention. So you're paying attention to the word before you as a word, so to speak. So suppose we have the sentence, the cat chased the mouse. When processing the word chased, the transformer simultaneously examines the cat chased the mouse rather than relying only on previous hidden states. So consequently, important relationships are learned immediately. This dramatically improves long-range dependency modeling, training speed, parallel computation, overall accuracy. Unlike recurrent neural networks, transformers then process the entire sentence simultaneously, making excellent use of modern GPUs and TPUs. So this single innovation transformed modern artificial intelligence permanently. So let's talk about self-attention now. What is the core innovation when we talk about core? I mean, this self-attention, talking about transformers. Now, the self-attention rather enables every token in a sequence to determine which other tokens are most relevant, right? So each word is transformed into three vectors. You have the query vector, you have the key vector, and you have the value vector. So the attention score between two words is computed by taking the dot product between the query and key vectors. So score. So you have a score for attention. So you score each attention by multiplying the query vector by the key vector. And then to stabilize that training now, the scores are divided by square root of d sub k, where d sub k is the dimension of the key vectors. So, I mean, if you have dimension so where this obtains the dimension of the key vectors for sure. So the attention weights are then obtained using the softmax. So you have you get the score, divide the score by you stabilize the score, stabilize training by dividing by this. So it's a kind of normalization, and then you can calculate the softmax, which is all about probability here. So the attention weights are obtained using the softmax function. So alpha is softmax QKT over square root of dk. So finally, the output becomes this. You have attention as a function of the query, the key, and the value, and that is equal to the softmax of the normalized attention score multiplied by the value by the value vector. So this single equation is the mathematical foundation of modern large language models, basically. So imagine this example. Suppose the sentence, the cat chased the mouse. When processing chased, suppose the attention weights become this now. You have the cat chased the mouse, so 0.04, 0.43, and all of that. Mouse 0.41. So notice that the model automatically focuses on cat and mouse because cat is 0.43, mouse has 0.41 as weight. So these are the most two informative words there. So the selective focus is why transformers understand language much better than earlier architecture. So transformers can just look at a sentence and say, oh, okay, from this sentence alone, we should pay attention more to cat and mouse here because they are like the key things holding the whole sentence together. And then we go to queries, keys, and values. We explain queries, keys, and values. So to understand self-attention, we must first understand the three vectors generated for every token. So every input embedding is multiplied by three different weight matrices to produce query. So every input embedding be multiplied by different weights matrices to produce the query, the key, and the value. So mathematically, query is actually the input vector x multiplied by the weight for the query, and then the key is the input multiplied by the weight of the keys. The value is the input value and the weight of the values. So like I said, x is the input embedding matrix, wk is the query weight matrix, wk is the key weight matrix, and wv is the value weight matrix. Each matrix is learned automatically during training like that. So all these things are done by the model itself. So the intuition here is that if you imagine this, that you're entering, imagine entering a library and you have a query. What information am I looking for? That's the query. So you go to a library with a particular focus in mind. Then the key is what information does each book contain? So, and then finally, what knowledge should be returned if a book is relevant? So that means maybe you go to a library, you want to learn about uh you want to learn about transformers basically, right? Then you now find different books on transformers. Maybe one book explains the formula of the transformer formula. One text talks about the history of transformers and everything. And the value you aim to get is what knowledge should be returned if a book is relevant. So if you have to pick only one book, if you read all the books, right? Maybe what you actually want is you want clear explanation on the formula about about attention, right? So at the end of the day, the knowledge to be returned with is you have a clear in understanding of every component of the attention formula. So every word asks a query, a question, which is query, and it compares with every other words or key. So you have what information am I looking for? So you check all the books available, and then you receive information from the corresponding value vectors like that. So you are looking for a particular information about transformers, then you find different books on transformers, and then maybe you browse through them, or you take a long time to read each book, and then at the end of the day, you get the information you want, which is the value you get from the books. So imagine an example, a sentence, artificial intelligence changes education. Suppose the query vector for changes is Q, which is 1, 2, and the key vectors are K, which is 1, 0, 0, 1, 2, 1, 1, 2. So the attention scores are computed using Q multiplied by the transformation of KT. So of course you have a 2 by 1 matrix multiplied by the transpose of this will be 2 by 4 because this is actually 4 by 2. So it will be 2 by 4. So 2 by 1, 2 by 4. This is 2 by 1. And then this is 2 by 4. I think that won't work well. Maybe, but we can do 2 by 1 and so you have Q K transpose. But I mean we have to make sure they are compatible to make sure to be able to multiply. So we can this is 2 by 1, right? So we can do KQT even or something like that. So to make sure they are aligned. So the larger the score, the more attention is given to that word. So as you compute this, you get a score. So the larger the score, the more weight the word carries. So does the model make focus primarily on artificial intelligence and education, while largely ignoring less informative words? Now we already talked about how you query an AI, and then since AI doesn't understand language, it breaks down the words into tokens and it assigns vector values to those tokens. So these are the vectors now. So when they are multiplied, then from there you can get the weight that that each one carries. Now we have the scaled dot product attention. So the dot product rather between query and key vectors means similarity. So they compute some kind of similarity. However, as vector dimensions become larger, the dot product also becomes very large. So large values cause the softmax function to become saturated, making learning unstable. So because of that, to solve this problem, transformer models divide the scores by square root of d sub k, where d sub k is the key dimension. So the complete attention equation then becomes attention as a function of query key and value is equal to softmax. So the softmax is a probability kind of thing. So softmax of qk transpose all over square root of dk multiplied by v, the value. So you have an example here. Suppose that qkt is 64 and dk is 64, then square root of 64 is 8. Then the scaled vector becomes 64 over 8, which is 8. Instead of 64, now the resulting softmax distribution becomes smoother and more stable. So without scaling, the model would assign nearly all probability to a single token, slowing learning and reducing gradient quality. So because if you have a token that has the biggest value, and imagine one has 2000, 4096, and then maybe the other ones have like five, the values are 5, 10, and all that. So by scaling, everything becomes better. So then we talk about multi-head attention. A single attention mechanism can capture only one type of relationship. Transformers therefore use multiple attention heads. So each head learns different linguistic patterns simultaneously. For example, so instead of the recurrent case and all that, we now have to do simultaneous job on different uh portions of whatever you're working on. So for example, head one may learn grammar, head two learns subject verb relationships, head three learns pronouns, head 4 learns semantic meaning, head 5 learns long distance dependencies, and the outputs from all heads are concatenated together. Mathematically, you don't have head I is attention, so the attention can go on simultaneously for different heads. So the complete multi-head attention layer is now multi-head of QKV instead of just having just one attention. So it concatenates all the heads from head 1 to head H multiplied by W0, where H is the number of attention heads and W power 0 is the output projection matrix, like that. Now, why do multiple heads matter? So consider the sentence. The students who won the award thanked the professor. Different heads may focus on student thanks, professor thanks, won award, grammatical structure. So you have different heads focusing on this, and then you have another one focusing on grammatical structure. Together, they build a much richer understanding than a single attention mechanism. So imagine positional encoding. Unlike RNNs, transformers process all words simultaneously, right? That's one of their superpowers, which was the problem with RNNs, LSTMs, and even G, what's that now? G something, I forgot. GP, no, not GPUs now. Yeah, we saw that initially as solutions to RNNs. We then had LSTMs and G something. That's what I'm trying to remember now. Vanishing gradients. Okay. Yeah, GRUs, gated recurrent units. Yeah, gated recurrent units. All right. So with that said, then we move on to okay. We now move on to positional encoding. Unlike recurrent neural networks, transformers process all words simultaneously. As a result, they do not naturally know the order of words. So consider sentence A, dog bites man. Sentence B, man bites dog. These words are identical, but their meanings are completely different. So to preserve order, transformers add positional encoding to every embedding. So the original transformer uses sinusoidal functions. So for even indices now, you have P of E, positional encoding of position 2i equals sign POS over that's position now over 10,000 raised power 2i over d. Then for odd indices now, you have positional encoding, position 2i plus 1 equals cos POS over 10,000 raised power 2i over d, where POS is the word position and d is the embedding. So the position of the word, that's what POS represents, and d is the embedding dimension. So these periodic functions allow the model to distinguish nearby and distant positions while generalizing to longer sequences than those seen during training. So, I mean, this helps the whole learning and prediction process as may be required. So, and then imagine an example here. Suppose the sentence is AI changes the world. The embedding becomes AI changes the world. AI is one, but position one, change is two, three, the position three for D, world is four. So the positional vectors are added to the word embeddings before attention is computed. So that shows, so if you are at position 72, you can at least still see AI in position one like that. So then 30.11, transformer encoder architecture. The encoder converts an input sequence into a rich numerical representation. So each encoder block contains six major components. You have input embedding, positional encoding, multi-head attention, residual connection, and layer normalization. And then you have the feed-forward neural network. The output of one encoder layer becomes the input to the next encoder layer. Of course, as we already understand, you have the idea of forward propagation, which leads to a prediction, and whatever is predicted, based on whatever is predicted, you compare with the real outcome, and then a real expectation, right? And then you have the loss, the error, and then that goes into back propagation, which is good for the learning process and to improve the weights and biases. So the output of one encoder layer becomes the input to the next encoder layer. So that's like the same pattern. So mathematically, residual connection is y is equal to x plus attention of x. So then for layer normalization, you have layer norm y is y minus mu over square root of sigma squared plus epsilon, where mu is the mean, sigma is the standard deviation, epsilon is the small constant for numerical stability. So I mean, we have this in programming. You have a small value in case you take something like log, you don't get an undefined result. Like that. So you don't have the feed-forward network. FFN of X is W2 Reluda's rectified linear unit, which is the default activation function in AI, except of W1X plus BI plus B2, like that. So the question is why residual connections matter. Deep neural networks often suffer from vanishing gradients. Now, residual connections provide a shortcut, allowing gradients to flow directly through many layers. This enables transformers with dozens or even hundreds of layers to train successfully. Then we have transformer decoder and also regressive generation. While the encoder learns representations of the inputs, the decoder generates outputs one token at a time. So large language models such as GPT primarily use decoder-only transformers. So during generation, each new token depends only on previously generated tokens. So mathematically, probability of x1, x2 up to xn is the summation of or multiplication of all probability of this current token given the previous tokens. So this decoder uses masked self-attention. So masking prevents future words from being seen during training, like that. So, for example, suppose the sentence is artificial intelligence changes everything. When predicting changes, the decoder can only attend to artificial intelligence. So it cannot see everything because that's what belongs to the future. So that's masked attention, right? Like we said, masked self-attention. So this masking strategy enables autoregressive text generation. So imagine this example. We have a prompt. Machine learning is, right? The decoder predicts transforming. The sentence becomes machine learning is transforming. So the decoder now predicts the next word using the updated sequence. So this process repeats until an end of sequence token is generated. So this iterative prediction mechanism powers ChatGPT, Claude, Gemini, and most modern large language models. Now, why transformers scale so well? Why do transformers scale so well? One of the greatest strengths of transformers is that they become more capable as we increase three resources, as we increase model parameters, training data, and computing power. So this observation is known as the scaling laws of deep learning. So unlike previous neural network architectures, transformers continue to improve predictably as they become larger. In general, performance is F of parameters, data, and compute. Although the exact relationship is complex, increasing three factors increasing these three factors usually leads to lower prediction error and better generalization. Of course, we are going to have to do more computation and it's a bit more complicated. Now, why scaling works now? Large models can learn more complex patterns, memorize less and generalize more, develop richer internal representations, solve tasks that were never explicitly trained to perform, solve tasks they were never explicitly trained to perform. These surprising behaviors are known as emergent abilities. Examples include translation, coding, mathematical reasoning, summarization, logical inference, and scientific writing. So imagine this example now. Suppose we train three transformer models. So you have a small, medium, and large model with parameters 100 million parameters, 1 billion and 100 billion parameters, and the accuracies are 81%, 89%, and 96% respectively. Although large models require significantly more computation, they often achieve dramatically better performance. So this explains why modern large language models contains billions or even trillions of parameters. So we then have parallel processing. So the secret behind transformer speed now is parallel processing. Unlike recurrent neural networks, transformers process an entire sequence simultaneously. So consider the sentence, artificial intelligence is changing education forever. So for recurrent neural networks, you have artificial intelligence is changing education forever, and then each word must wait for the previous one. But in transformer processing, you can have artificial intelligence, so and then you have self-attention layer applying to everything at once. So every word then is processed at the same time. This allows modern GPUs and TPUs to perform thousands of computations simultaneously. And then talking about computational complexity now, for a recurrent neural network, processing time increases approximately linearly with sequence the length. So transformers have higher attention computation but allow almost complete parallelization during training. As hardware became more powerful, this parallel design proved far more efficient than sequential recurrence. Now, why this matters? Training GPT-3 involved processing hundreds of billions of words. So without parallel computation, such training could have required an impractical amount of time. So parallelization is one of the major reasons transformers replaced RNNs. So parallelization is one key thing we have here. And then attention to words like that. So Python example, computing self-attention here. So the following example demonstrates a simplified implementation of self-attention using NumPy. So NumPy is for numerical computation in Python like that. Can this just go? Okay. Now we have this. So you have a query matrix 1, 0, and you have a key matrix 1, 0, 0, and 1, 2. So like that. So that's the 1 by 2 matrix, and this is a 3 by 2. So which can then become a 2 by 3 when you transpose. So then you have the value matrix 10 to 3, 8, and 6, 6. So if you compute now the scores, so you have Q multiplied by K transpose, and then you can then have the scores and then square root of the shape. That's for the dimension, the normalization for scaling the scores. Then you have the softmax. So softmax takes the exponent of each score and then that takes you don't have the weights over the sum of the weights now. So the attention output is then given. So by the time you run this, you get the attention scores now 0.70, 0.70071. Then you have the weights 0.4, 0.1, and 0.40. And then you have the output 7 and 4.79 like that. So the explanation here is this. The program follows the following steps. It computes query key similarity and scales the scores, applies the softmax function, and then this uses the attention weights to combine the value vectors. So this is essentially the same sequence of operations performed inside every transformer layer used in ChatGPT, Claude, and Gemini. So although industrial models contain billions of parameters, the mathematical principle remains exactly the same. So, and then we have applications of transformers now. Transformers are no longer limited to language processing. Today, they power nearly every major branch of artificial intelligence. So, like I said, I like to see artificial intelligence as having 5 branches. And of course, somebody else may tell you another thing. So, for me, I see artificial intelligence branches as machine learning, natural language processing, robotics, computer vision, and expert systems. So for natural language processing like ChatGPT, Claude, Gemini, machine translation, text summarization, question answering, and document retrieval, you have transformers working well here. Then talking about computer vision transformers, this divide an image into patches and processes them as tokens. So you have applications including image classification, medical imaging, object detection, and face recognition. Then for speech processing, you have speech recognition, speech synthesis, voice assistance. Then for bioinformatics, you have transformers used in protein folding, DNA analysis. In fact, I think a protein folding uh, work won the Nobel Prize. Something that couldn't be done before machine learning has now been done. Then you have DNA analysis, you have drug discovery, and in robotics, you have robot navigation, decision making, and human-robot interaction. So for scientific computing, you have climate modeling, astronomy, material science, chemical simulation. Transformers have become the universal architecture for learning relationships within complex data. So, let's look at ChatGPT, Claude, and Gemini as they play into the whole transformer talk. Although developed by different organizations, ChatGPT, Claude, and Gemini, of course, ChatGPT by OpenAI, Claude by Anthropic, and Gemini by Google, all rely on transformer architectures. So, for instance, ChatGPT, developed by OpenAI, uses decoder-only transformer. So it uses decoder-only transformer models trained with next token prediction followed by instruction tuning and reinforcement learning from human feedback or related preference optimization methods. Of course, each time you prompt an AI, you're actually helping it to learn, right? That's the human feedback part. So applications include programming, writing, mathematics, data analysis, research, and education. Then we have Claude, which is developed by Anthropic, also built upon transformer technology. It is designed to produce helpful, honest, and safe responses while handling extremely long contexts. Applications include legal analysis, coding, academic writing, business documents, and long document summarization. And you have Gemini developed by Google, built using advanced transformer-based multimodal architectures, and it can process text, images, audio, video, and it can code, making it a powerful multimodal artificial intelligence system. Although these systems differ in training strategies, safety methods, and engineering details, they all rely on transformer architecture introduced in 2017 by Vaswani et al. Google staff, Google researchers, that is. Now, building a small transformer PyTorch. Now, let's try to do that. So you have PyTorch provides built-in transformer models, and the following example constructs a simple transformer encoder. So import touch, we are using Python. So import touch dot neural network, touch dot nn as nn, then encode layer. So for the encode layer, now you bring in the function transformer encoder layer, then the model 128, D model, then N head 8. That's attention heads now 8. Then D, that's for the normalization, that's 128. And then you have the batch first is true. Then transformer and then transformer dot encoder. They have the encoder layer and number of layers to be 6. Then for the batch size now, you have 4, sequence length is 20, embedded dimension is 128. Then so you now throw in all this 428 by 128. Then output transformer X, and then you have the touch size to be 420, 128, like that. So this is like to check if what you've done is cool. Now, the explanation here, 4 represent the batch size, 20 represent the sequence length, 128 represents the embedding dimension. Each encoder layer performs multi-head attention, residual connection, layer normalization, feed-forward network, exactly as described in the original transformer architecture. Stacking many encoder or decoder layers creates the foundation of modern large language models. So in summary, transformers fundamentally change artificial intelligence by replacing sequential processing with self-attention. So transformers have replaced sequential processing with self-attention, and the major reasons for their success include excellent sequence understanding, long-range dependency modeling. So you can, every word has a position. If you're processing words, for instance, and then you can then locate each of them, like that's included in the process. So you have parallel computation instead of sequential training, and then you have efficient GPU utilization, that's graphics processing unit utilization efficiently, excellent scalability, strong transfer learning, emergent reasoning abilities, and support for multimodal learning. So you then have some key equations here. So you have the sequence probability that you get a particular token given the previous tokens, and then you have the query, which is computed by the input matrix multiplied by the weight matrix, and then same for the key and the value, and then you have the scale dot product attention, so which ends up being softmax of the score over the normalized score multiplied by the value, and then you have multi-head attention, and that's why the whole idea of parallel competition comes in. So you have many things happening at the same time and then put together at the end of the day. So by now you are now able to understand. So you are now able to explain why RNNs and LSTMs were replaced, right? So RNNs came first, and then LSTMs and GRUs, gated recurrent units, came later. They improved on RNNs, but they weren't good enough until attentions transformers came. So describe how self-attention works, which we talked about. Explain queries, keys, and values. Understand positional encoding. Explain multi-head attention. Describe the transformer encoder and decoder. Explain why transformers scale successfully, and build a simple transformer in Python. Understand why ChatGPT, Claude, and Gemini all rely on transformer architectures. So the transformer is the foundation upon which modern artificial intelligence is built. So mastering it provides the conceptual framework needed to understand today's most powerful AI systems and many of the innovations that continue to shape the future of machine learning. So we have our practice problems now, and I'm going to solve 2 of them as usual. So here I'll do questions 3 and question 5, questions 3 and 5. So here we can see questions 1 and 2. Solve the following problems without referring to the lesson notes unless otherwise stated. Justify your answers clearly. So you have 1 and 2. Then we have 3, 3, 4, 5 now. So I'm solving 3 and 5. So 3 says, assume QKT is 18695 and DK is 9. Compute the scaled attention scores before applying softmax. Then 4, explain why the softmax function is applied after computing. Then 5, a transformer contains 16 attention heads. Explain 2 advantages of using multiple heads instead of a single attention head. I think we've talked about that amply. So you have questions 6 to 9 right here. Questions 6 to 9. Then you have questions 10 to 12 here. 10 to 12. Then you have 13, questions 13 to 16. Then you have 17. You have 17 to 20. Question 17 to 20. Or let me just show 17 to 19. Yeah, 17 to 19. Good enough. And then 20. All right, so let's go and take questions 3 and 5 as we bring this home gradually. So I come here. So we have problem 3. So assume the score QK transpose. QK transpose is 18, 6, 9, 15, and D sub K for normalization is 9. So we need to compute the scaled attention, scores before applying softmax. Okay, so we go for the solution. So we know that the scaled dot product attention first divides every attention score by square root of D sub K, like that. So since D sub K is 9, we have square root of D sub K to be square root of 9, which is equal to 3. So then, or we can say therefore, Q K transpose over square root of dk is equal to 1 over 3 into 18, 6, 9, 15. 18, 6, 9, 15, which is simply the same thing as divide 3 by 3. So that is 6, 2, 3, 5. 6, 2, 3, 5, like that. So we haven't applied softmax here. So if you apply softmax, it's another thing entirely. So this is what we are required to do. So here we just go ahead and say that these are the scaled attention scores, that will be passed, into the softmax function. And of course, to do the softmax function, you need to get the exponent of each one, right? We get the exponents of each one, and then we get the total exponent at the end of the day, and then we assign the weights So the interpretation of all this is that the first query attends much more strongly to the first key, right? So this is the biggest, right? To the first key than to the second key, which is 2 here. So this is stronger than this. Then the second query, so this first query, this is second query. The second query gives greater attention to the second key. So this one carries greater attention than this. So greater attention than the second one, like that. So the second query gives greater attention to the second key 5 than to the first key 3. So scaling prevents excessively large values, making the softmax function more stable during training and improving and during training and improving gradient flow. So that's question 3 right there for us. So let's go for question 5 now. So question 5, or let's say problem 5. So for problem 5 now, it says a transformer contains 16 attention heads. 16 attention heads. Explain two advantages. Explain two advantages of using multiple heads instead of a single attention head. So we can go for the solution. I think I want to use this now. The solution. Of course, we know that using multiple attention, using multiple attention heads allows a transformer to learn different types of relationships at the same time. So we can learn different types of relationships at the same time using attention heads. So with that said, so we can talk about the advantages. So advantage one. So you learn different features, So different heads can focus on different aspects of the input, such as grammar, word meaning, long-range dependencies, and subject-verb relationships. So you can learn different features like that. So what this does then is that this gives the model a richer understanding, of the sequence, like that. Then another advantage is this, that we have advantage two. That gives better accuracy. So combining information from multiple heads enables the model to capture more context than a single attention head, leading to more accurate predictions and improved performance on complex on complex tasks. So in conclusion, multi-head attention improves the transformer's ability to understand language by learning multiple relationships simultaneously, making it more powerful than using a single attention mechanism. So with this, we come to the end of this interesting video about um transformers, right? Which has changed why how, and that is we have seen why transformers replaced every other AI model. Because I mean, starting from recurrent neural networks that had to be sequential and then followed by uh, long short-term memory models, and then of course gated recurrent units. So transformers came to revolutionize the whole thing. So try your hands on the problems once again. So here you have one and two. You can see one and two clearly here. One and two, three and 3 to 5. Okay, I guess that was too fast. One and two, 3 to 5, 6 to 8, 9 to 11, 12 to okay, 12 and 13, 14 to 16, 17 to 19, and then 20. So let me know how helpful this is for you. And if you have subscribed to this channel already, I thank you very much for being here. If you have subscribed to this channel already, thank you. And if you have not subscribed, why not go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of this channel by clicking on join. That gives you special privileges you will find when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.